I'm not just going to review a couple more projectile motion problems, just because I really want you to understand this as deeply as possible. Because the rest of physics that we do, the rest of mechanics, a lot of it really just depends on your understanding of projectile motions, and hopefully this will be intuitive for you after some point. So let's just go back to a problem we did before. Let's say that I'm at the top of a building, and I take a rock or a ball, and I don't recommend that you do this, and I drop it. I drop the ball. And let's say that I know that the building, that the height, so that the building is, well, I don't know. Let's say it's a very tall building. Let's say it's well, let's say it's not too tall. Let's say we're throwing it from the 10th story, so it's roughly 100 feet, or that's about 30 meters, right? 30 meters. So the ball is going to go 30 meters down. So the change in distance is going to be minus 30 meters, right? The ball is going to fall 30 meters. Now, if I ask you, hey, how fast is that ball going to be when it right before it hits the ground? Well, there's two. I could rewrite all the formulas, but I think hopefully you know them by now. But there's two kind of interesting formulas we might use, and I'll also show you maybe how to do this more intuitively. But there's VF squared is equal to VI squared plus 2AD. And then and this is 2 times delta D, right? Whoops, plus 2A times change in distance. Sometimes I'll just write that as distance. And then there was change in distance is equal to the initial velocity times time plus acceleration times squared over 2, right? And then there was the other ones, change in distance is rate times time, and velocity is is acceleration times time, and you know about all average velocity, et cetera, et cetera. So one of these formulas I think might strike you as immediately useful to what we're trying to figure out, because we're trying to figure out what the velocity is when you hit the ground, right? We want to know what the final velocity is. We know the initial velocity. The initial velocity is 0, right? We're just letting it go. And then what's the acceleration? Well, the acceleration is gravity, which is equal to minus 10 meters per second squared. So we could use this formula because we know VI, we know acceleration, we know change in distance, so we could solve for velocity. So we get VF squared is equal to VI squared. Well, that's just 0, right? Times 2 acceleration, so that's minus 10. And then what's the distance? Well, the distance is minus 30, right? Change in distance is minus 30. So you get VF squared is equal to, 10 times 30 is 300 is equal to 600. And we know, let's see. So if I took 600 square root, so roughly 24.5 meters per second. So VF is equal to 24.5, approximately equal to 24.5 meters per second. Now, if we wanted to know, well, how long did it take the thing to hit the ground, or how long should it take the thing to hit the ground? Well, then we could use this formula, right? Because we know the change in distance, we know the initial velocity is 0, we know the acceleration, so we could just solve for t. So change in distance, I said, was minus 30. Minus 30, right? The ball went down 30 meters, so we could say minus 30. And remember, let's see. Let me change the colors because I want to make sure you know which formula I'm using. So I'll do it in that color. Minus 30 is equal to the initial velocity is 0, so the initial velocity times anything is 0, so this term cancels out. Plus AT squared over 2. So what's A? A is minus 10. Minus 10 divided by 2 is minus 5. So it's minus 5t squared. And so you divide both sides by 5, and you get t squared is equal to 6. And once again, use the trusty calculator. The square root of 6 is roughly 2.45 seconds. T is equal to 2.45 seconds. Pretty neat. Using these two formulas in about 3 minutes, and we probably do it faster if we weren't explaining it, so you could do it really fast on an exam. I just said I drop a ball from a building that's what did I say, 30 meters high. Now, very quickly, we were able to figure out how fast it was falling when it hit the ground, and how long should it take for it to fall. And if I were to give you one of the other pieces of information, if I told you that the ball took 2.45 seconds to fall, and I didn't tell you the distance, then you could have figured out the distance based on that information using the same formula. So hopefully that makes some sense. So let me do. Actually, I'll leave it there right now. I just wanted to show you that when you actually just go straight to the formulas and you don't do all of the kind of meandering explanations that I tend to do, which I do for a reason. I do them to give you an intuition. But when you just go straight to the formulas, these equations, these problems don't really take much time. But with that said, let me show you how to do it intuitively if you forget the formulas. So once again, I'm dropping a ball. It's a 30-meter building, right? And I want to figure out what the speed is when it hits, and how long did it take to fall. Well, let's just start with our basics. Let's say I just had amnesia, and the only thing I remember is change in distance. Change in distance is equal to rate times time, or average rate or average velocity times time. And I know that change in velocity is equal to acceleration times time. If I say if I know that my acceleration is constant, otherwise it would be kind of the average acceleration. But this is all you have to know, and I'm going to show you right now. So we know what the change in distance is, right? The change in distance. And just so not to confuse you, we're doing the exact same problem, but I'm just showing you that you didn't have to memorize the formulas, although it might be faster if you do. So the change in distance is minus 30 meters, right? So let's plug that in straight. So we know that minus 30 meters. This is what I'm going to use. Minus 30 meters is equal to the average velocity times time, right? Well, what's the average velocity? Let's see if we can figure that out. Well, we know the average velocity is just the average of the initial and the final velocity. Well, what's the initial velocity? Well, the initial velocity is 0. Vi is 0. The final velocity is, well, it's the final velocity. We don't know that yet. So what's the average velocity going to be? It's going to be the average of these two numbers. So the average velocity is going to be, this is a little too bloody. I don't like this color. The average velocity is going to be the final velocity plus the initial velocity over 2, which equals Vf over 2, right? So let's put that into our formula. So minus 30 is equal to the average velocity is just the final velocity divided by 2 times time. And now you're saying, but Sal, we still have two variables. We can't solve for either one of them, right? Well, if we could write time in terms of final velocity, then we could solve for final velocity. So let's try doing that. So let's use this equation right there. Change in velocity is equal to acceleration times time. What's the change in velocity? It's the final velocity minus the initial velocity. And that equals acceleration. Acceleration is minus 10 meters per second squared times time. And what's the initial velocity? That's 0, right? So we know that Vf, this is 0, is equal to minus 10t. And if we wanted to write the other way, we could say t is equal to minus Vf over 10. Right? I just rearranged this equation. Now I could take this and substitute it back into this equation, and I get minus 30 is equal to Vf over 2 times t, which is this right here. So times minus Vf over 10. And if you solve this, you get minus Vf, well, you get minus Vf, you essentially get the exact same thing we got in the previous problem. You get Vf squared is equal to 600. I'm skipping some steps just because I'm running out of time. And you get the same answer, whatever, 24.5 seconds. I just wanted to do that because I wanted to show you, you really just have to memorize these two things. And then you can derive all those equations on the fly, although it can be faster to know them ahead of time. But these these are the only two things that we're ever really using. Those other equations are just derivations of them. I'll see you in the next presentation.